Welcome to our Water Resources Special Interest Group meeting.
So there's going to be three main sections today, starting off with a motivation for this work, getting at why are we using deep learning to extract channel networks and why is it important to actually extract channel networks. Then we'll move into a background of deep learning. So what is it at a high level and how is it useful for this task? And then finally, we're going to go into an application of a deep learning workflow in Alaska and look through some preliminary results. So the motivation for this work begins with just the importance of locating streams. Stream mapping is critical for hydrologic modeling. So that includes stream flow modeling, sediment transport, water quality. Knowing where streams are is also important for emergency management, such as flood risk assessment, and then also ecological monitoring and management. So things like wetland protection and terrestrial and aquatic habitat conservation. So given that there is so much importance in knowing where streams are, it's also really important that we have some accurate inventories of channel networks. So that motivates this ongoing effort that's happening right now to update some stream data sets, such as the National Hydrography dataset. And the process of updating this data, especially at a national scale, can be very costly and time consuming. And that's where there's a lot of potential for incorporating automated techniques, which can help streamline some of those manual processes by providing a starting point or an initial screening of where streams are likely to be. And moreover, just having these repeatable and automated workflows in place will help us out in the future, because although we're updating our stream data sets now, this won't be the last update. So when the landscape changes or when new and better data is available, it's going to be good to have these automated techniques in place that can help us along. And finally, where does the added benefit of artificial intelligence or deep learning come into play? So in general, artificial intelligence or AI frameworks are very good at incorporating many data sources in an objective way. So it's very good at using things like LiDAR elevation data and imagery data that can help distill all of these indicators where streams are likely to be. And then these data are used to learn what combinations of those data indicate a stream versus not a stream. So that's kind of the basis of artificial intelligence. And then deep learning, which is its own subset of our artificial intelligence, is unique in that while it's trying to consider, which data indicates a stream, it's also considering the spatial context of what makes something a stream. So with deep learning, the training process takes into account that if this area looks like a stream, it's even more likely to be a stream if it's surrounded by other stream-like features. So just knowing that a stream is part of a larger object. And to illustrate how deep learning is exactly doing that, we're going to go through just a high-level introduction to deep learning. So on the left here, we have a black and white image, or consider it a binary raster with just 0 and 1 values. And let's say that we want to find where a diagonal pattern exists within this image. So on the right, we have some filter that we're going to use to try and identify where that pattern exists. And what deep learning does during something called a convolution is it passes that filter all along an image as a moving window, as seen here. And as it's passing that along, it's doing a combination of overlapping numbers within that window. So that's where that multiplication sign comes in there. And after this filter passes all through an image, then we get some transformed version of our input data. And this transformed version of the data is essentially showing us where that diagonal pattern exists because they show up as relatively higher values. So let's bring that together into a basic deep learning application. So let's say that we want to train a deep learning model to tell us when an image of the letter X comes up. So to do that, we would pass in some labeled examples of what an X looks like. And the deep learning model would start to create all of those different types of filters and pass it along the image until it recognizes that an X should have a diagonal going in 2 directions and a crisscross in the middle. And after that training phase is completed, then we have this trained deep learning model that we can use to identify other letters. So an example of that would be, let's pass it some image of an unknown letter as shown here. And if that model passes the same filters and finds those X characteristics, so the different crisscrosses, then it knows to classify that image as an X. And there are basically a lot of different types of deep learning models that are all distinct based on the way that they come up with those best characteristics or filters to apply. And the specific deep learning model that we're going to be using and talking about today is called a multitask road extractor model. So the multitask road extractor deep learning model is inspired by human learning patterns, where when we set out to learn a new task, we're really learning a series of subtasks in parallel. So if you think about when you learn to ride a bike, you're at the same time learning how to balance the bike, how to navigate the road, and how and when to brake. So this model, as the name suggests, was created for extracting road networks, where the subtasks that it's programmed to learn are, 1, how do we identify road pixels? And 2, how do we trace lines to connect them, because we know that roads are part of a larger network. And if you think about it, these principles translate over really well to stream identification, and that's where this workflow really came from. So with the rest of the time, we're going to go through a proof of concept for applying this multitask road extractor model to stream extraction. And that brings us into our deep learning application. So the study area is in Alaska, where there is actually a pressing need to start mapping and digitizing streams. And in this application, we have 2 main input data sources. On the left is the first one, which is a digital elevation model. And having this topographic information is very useful for identifying streams, because from that data, we can model things like where in the landscape is water likely to flow to or away from. And we can infer where the groundwater table may be very close to the surface, and therefore where it may be saturated. So from the elevation data, that is where we're going to provide the model ways to start learning what characteristics point to a stream versus not a stream. And the complement to that is a set of verified streams, which is our second source of input data. So on the right, we're just seeing a map of all of the known streams in this area, and we're going to pass just a subset of these streams to the deep learning model so that it can look at an example of where these streams are and what the underlying characteristics are. So it can start to learn what those relationships and dependencies are. So from that elevation data, we're actually going to derive some different indicators that are specific to stream extraction. So if we zoom in and kind of compare to the aerial imagery, and you can see visually where that stream likely is, the first derivative that we get from the DEM is called the topographic wetness index, or TWI. And TWI considers the slope and flow accumulation in an area to compare its tendency to accumulate water to its tendency to drain water. So in this way, it models area as being wetter or drier. And comparing to the aerial imagery, we can see that TWI shows some wetter areas along those streams and stream banks. The next derivative that we're using from the DEM is called the topographic position index, or TPI. And this index is essentially looking at the elevation of one cell in your image or your raster, and it's comparing it to the cells around it. So is this cell higher or lower than its neighborhood? And in that way, TPI is meant to identify to what degree is something a ridge or a valley. So if we look at our zoomed in example here, we're seeing that some values are picked up along those stream banks by the TPI. And our third and final derivative that we are feeding our deep learning model is a geomorphons layer. So geomorphons are also derived just from the elevation data, and it does kind of a similar task as TPI, where it's looking at the elevation of one cell compared to its neighborhood. But on the back end, it's doing a little bit more of a complex assignment of what neighborhood should I be looking at. And in the end, we get these geomorphon classifications. So you can see this area classified as things like flat or a ridge or a valley or a foot slope and so on. So these 3 predictor variables are essentially being stacked up and squashed into just a single raster that is containing the information for all 3 of them. And this is what the deep learning model is going to use to start to set some rules for, this combination of these 3 indicators means a stream versus not a stream. And that brings us to the end of kind of the data pre-processing phase and into the actual deep learning workflow using our Esri tools. So the first step in this deep learning workflow is to prepare the training data. And we do that using the export training data for deep learning tool. So in this tool, we are using that composite raster where we have kind of squashed together all of our topographic derivatives. And we're also feeding it our set of verified streams. And what this tool is doing is essentially breaking up these rasters into a bunch of image chips that are paired together. So when the deep learning model goes to train, it knows that this image chip with streams in this configuration are lining up exactly with this combination of topographic data. And further, we pass in this little yellow polygon that we're showing to tell the model only use image chips within this area and learn from those. And then everything else we're going to leave as an objective way to see how well our model did when it actually makes some predictions. So from there, we execute the model training phase, and this is where we start to use some Python code. So these are all different modules from the arcgis.learn library. And we go through the steps of preparing our data, loading the multitask road extractor model, and we start to get some of our model finer parameters, such as finding the learning rate. And then from there, we finally go and train our model. So in this example, we are letting the model train 50 times. And after that training is complete and our deep learning model is saved and packaged, the program also outputs some handy things that we're seeing on the right, like model metrics and some sample results that we can go back and refer to. And the last step of this deep learning workflow is to now apply our newly trained model to the rest of our area and generate some predictions. So now we're moving back into some user interface tools, and we're going to run classify pixels using deep learning. So here we are giving the model all of those topographic derivatives that we showed before and pointing it to that Esri model definition file that is storing all of the rules and relationships and dependencies that the model learned during training. And the output of this tool is our set of predicted streams. So we're seeing for the entire study area in red where the model predicted streams to be, both within the area that it got to learn from, and then outside of there, which kind of represents area that is totally unseen by the model. We're going to take a little bit of a closer look at some of those results and just talk about them. So if we zoom into these two subsets, what we're seeing in both images on the right is the aerial imagery, and then on top of that, the predicted streams, which are shown in that red shading all along. And then on top of our predicted streams for reference, we have the verified streams or the testing streams. So that's in the blue lines there. So in this way, we can compare how well do the predicted streams line up with our known streams. And that way we can get some visual idea of how good our model was. So we are seeing some examples where the model did really well in maintaining that connectivity of a channel network where we have one continuous stream prediction that's lining up very well with the verified streams. And then we also see some shortcomings where it looks like some of those channel segments were disconnected, and then also some lower order or smaller streams seem to not be picked up by the model. And some of the errors like this could be addressed by things like supplying the model with some additional stream indicators, so maybe some imagery data to learn from or some vegetation data. We could also improve this model by reconsidering the scale of topography that we're capturing. So if some streams are much smaller, maybe we need to give the model some topographic data that will model these slimmer channels. And finally, you could always improve some of these results by just improving the quality of your training data. So feeding it more types of streams and more streams in general. All right, and now just last slide here to go over some takeaways from what we've seen today. So first off, the deep learning results from this workflow could be useful in practice as some initial screening of channel networks, all essentially to streamline a manual process. So some manual digitizers could go in and focus on these areas that the model has picked up rather than all of the area. Or they could also consider it as some ancillary data as part of their overall process. Secondly, we also showed that our proof of concept shows that there is potential for deep learning to support stream mapping as this emerging automated and repeatable workflow. And finally, we showed how the Esri deep learning toolset can be used to implement some new and emerging workflows such as this one for stream extraction. With that, just some acknowledgement to other contributors within Esri who helped out with this demo and some resources I can share. And I will pass it back over to Krista.